All right. So as Laura is trying to add you as a co-host, and so hopefully you can share your slides. Let me just welcome everyone to this CCAM's presentation. We're very glad to have our first CCAM presentation of this academic year through Zoom. As you all know, today's speaker is Dr. Derdei Bichara from Mathematics Department at Cal State Fullerton. And Bichara is a mathematician with broad interests in mathematical biology, modeling infectious diseases, and complex models for pandemics. And indeed, through working with him for the past few months, I thought it would be fantastic to have him to talk about the basic concepts of mathematical modeling of pandemics. He has published extensively on this area, on many other infectious diseases in the past, and it's incredible when the COVID hit the States. I was looking for a collaborator to work with, and I just realized we have a top level mathematician with years of experience in this area in our midst, in our department. So it's fantastic. So since we're slightly late, let's just start with the presentation. Bichara, do you want to share your slides with us?
Yes, please.
Fantastic.
All right. Thank you very much. I want to thank you guys to chime in and to see what's going on with what we are trying to do. And also, I'm trying to give like a very brief introduction of the mathematical model in how to try to model epidemics. Okay. And I want also to thank Sam for inviting me to give this talk. All right. All right. So these days we've heard a lot of stuff, a lot of buzzwords: pandemics, outbreaks, epidemics. And what's really the difference? What's the big difference between outbreak, epidemics, and pandemics? So outbreak is a small disease that will pop up in one small community and disappear after some time. Okay. And pandemics is a more global outbreak. Okay. If this outbreak spreads through many communities or many countries, in that case, it will become a pandemic. And what about epidemic? Epidemic is basically an endemic that will not go away. It will stay within the community. Let's say the flu, it will always be around. Okay, so that's the big difference between these three terms. All right, so let's try to see where the mathematical models of this pandemics, outbreak, and epidemics are coming from. So one of the early models in biology in general or in population dynamic is how population evolve over time. Okay, so suppose that we have N of t, right, which is a population at time t, and suppose that we have B and D as birth rate and death rate. So at time t plus delta t, what do we get? We get N of t plus delta t is exactly equal to the previous population plus those who are born minus those who died. So if you put them together, we'll get this. And if we take the limit as delta t goes to 0, we'll get this nice differential equation. Okay. All right, so if we let R equal B minus D, So this is the birth rate minus the death rate. So this will give us the growth rate. So this is one. And we'll have a nice differential equation of first order and dot equal to Rn. So this is a very simple model, of course. And the idea is people try to see how this fits the actual value. And of course, all of these are approximations. All right, so in 1965, right, so the US Department of Commerce have tried to estimate the growth rate of the population, which happens to be 2%. Sounds good. And at that time, the Earth population was 3.34 billion. Okay. So of course, if we have this, right, so this n of t is equal to n0 exponential of rt. And as we can see, so this goes to infinity if r is positive, and 0 if r is negative. Okay. All right. Or if you want this, it's also, if you don't have a time t equals 0, it will be rt minus t0. Okay. N of t0 if you want. So t0 could be anything. So this happens to happen in 1965. So in general, right, this is how the population evolved over time. If we suppose that our model is accurate, our initial the Malthusian model is accurate. Okay. All right. So now, if we are supposing this is correct, the US government wants to know when this population will double, the Earth population will double. So if you compute, all right, if you say n of t equal 2 times n0, which is 3.39, we'll get this. So this model projects that the Earth's population will double in 34.6 years. But this happens to be an excellent prediction, because in 2000, right, if you add 34 plus 65, you will get almost 2000. So in the year 2000, the Earth's population was exactly 6 billion. Okay. So what if we are trying to project in a distant future? So in 15, the Earth's population will be 200,000 billion if you are following this model. In 2660, we'll have 3 billion and a half, 3 million and a half billions. So that's a lot of people. Okay. So we want to see if these numbers are actually realistic. I mean, at the end of the day, they were realistic in trying to project when the population will double. All right, so the total surface of Earth happens to be 1,800,000 billions of square feet. 80% of it is covered by water. But even if we suppose that we are technologically advanced enough to live in every inch of our planet, right? So in 2515, the density would be, that's what we got here, 300,000, and of 2016 divided by the surface divided by the number of population. So here we'll get 9.1 square foot per person. Okay, fine, not bad, right? But in 2660, the density would be 1/2. That is 2 people per square feet. So we have to live on top of each other. That happens to be not possible, at least I think. So that implies that while our model here is nice in a shorter distance, in short term, it's completely unrealistic as time moves forward. Okay, and of course this one is very approximate model. We have included only the birth and the death rate, and again these are estimations. So one needs to kind of tweak the previous model to include some sort of competition. So we'll have something like this. So this one is a logistic model. One could solve it easily. That's Calc 2-3 level. Okay. So if we have this, what would be the limit as t goes to infinity? So the limit as t goes to infinity of n of t will be exactly a over b. Of course, this is assuming that the growth rate is positive. Okay. So that means the population will never exceed some sort of capacity. It will not explode. It will not have the explosion that we had here. Okay. So the graph will be, so for the exponential, that's what we got. And now for the logistic, we'll be getting something like this. Good. So at the beginning, they were both good, but as times as time increases, will not be able to, the exponential growth will be completely unrealistic, whereas the logistic model will give some nice estimation. And if we use the previous estimate where R equal 2%, right? So the logistic model will project 10 billion of people. So it says their population cannot exceed 10 billions. And right now we are at 7 billion. So it's not that bad. Okay. Maybe it will change. All right. So now that we have this, later, Ross, Kermack, and McKendrick try to use this type of models and try to capture the dynamics of diseases. Okay. So we have the first one to capture mathematically a type of disease is Ronald Ross, right? And he tried to understand malaria. And but before him, some people have shown that it's actually not caused by the bad air, but more by mosquitoes. So Ross, he definitely proved that the cycle of malaria is in mosquitoes. So mosquito will transmit to human, and human will transmit back to mosquitoes. Sound good? So what he did is he said, okay, so in order to get rid of malaria, because back then it was many people were dying because of malaria. So he said, in order to get rid of malaria, we need to suppress all mosquitoes. But the problem is, people say, no, that's not possible because that will create a sort of ecological catastrophe. Okay, so Ross was kind of said, okay, that's fine, but he was still convinced to his idea that in order to get rid of malaria, we need to eliminate all mosquitoes. So he needed some sort of quantitative argument. Okay, so what he did is he went and to do some mathematics. So because mathematics, you cannot really argue with it, right? So and this guy he's not even a mathematician. He's physical doctor, okay, a medical doctor. So he used mathematics to kind of show that we don't necessarily need to eliminate all mosquitoes, but all we need is to bring the quantity of mosquitoes below some sort of threshold. And that's where he theorized the so-called mosquito theorem. So he said we need only to bring it below certain threshold. And of course, his measure was successfully implemented, and malaria was eliminated in many places around the globe. Okay, so now a couple of his students showed up, and they want to know what's going on with not with mosquitoes in humans, but more with pathogens and viruses. Okay. So the first model they came up with is the simplest one, SI model. So we have let me use, we have S and we have I. So they divided the population into two categories: people who are healthy and those who are infected. Okay. So what they did is, if someone who is susceptible is in contact with someone who is infected, right? Because a susceptible person will interact with with all people. And among these, there are 1/n who are infectious. All right. So now, so that's the contact terms. Now, even if we had a contact, there's a likelihood that I might not get the infection. So we multiply by beta to say, okay, if a certain person meets someone who is infectious, and that this contact will lead to infection, so beta is the probability to get an infection once you get a contact with someone who is infectious. So, and what they did is simple input-output, right? And we suppose that after some time, people who are infected will also recover at a rate gamma. So we have a simple model like this, right? And here, if we take a closer look, right, n dot is s dot plus I dot, and it happens to be equal to 0. So n is constant. The total population is constant. So we could reduce the 2D ODE into 1D. Okay. So we replaced n s by n plus n minus 1. And we'll get something exactly as the logistic system, logistic ODE that we saw earlier. Okay. All right. So now by solving this, we'll get this. Because this one is a nonlinear system of differential equation, and it's difficult to solve. All right. So it happened that, if you remember, we said if A is positive, right? So if A is positive, that implies a limit as t goes to infinity is equal to 0, and the limit of I will be just equal A over B. But if it is negative, what do we get? So this will be equal infinity, and the whole thing will be just 0. So if the limit of I is equal to 0, then the limit of S equal 1. That means the infection will die out from the population, and everyone will get healthy again. Okay. Now, of course, the goal is to maintain this. How to keep A minus gamma less than 1. So you could see that also as beta over gamma is less than 1. So gamma, if you take a closer, gamma, what does it mean in terms of, it means the time in which you spend in the infectious class. So the time after which you recover basically, either through treatment or otherwise. Okay. All right. So this quantity is very important, as we'll see soon. So this one is called SI model. All right. Now there's another system is called SIR model, which is exactly as the previous one, but instead of recovering and getting susceptible again, you will become completely immunized. Once you recover, you will not get affected again. Okay. So now we'll have exactly the same, but now we have a 3 system. Okay. So again, this is actually the original model by Kermack and McKendrick. Right. Again, the coefficients are exactly the same. Gamma is the recovery rate, and beta is the transmission rate. All right. So of course, if you guys, so before we divide by n in the previous equation, but since the population n is constant, we could always scale our model to get rid of the extra parameter. Okay. All right. So now, so Kermack and McKendrick, they had the system, but they want to test this on an actual disease. And of course, the most difficult part is how to estimate beta and gamma. So back in early 1665, right, there were a plague in England, and particularly there's one small village called Am. So this village, they were hit by the plague, and they tried to quarantine themselves. They won't let anyone in, and no one will leave. And they kept detailed record, like how many people have died, how many people have recovered, and so on. All right, so typically it's very difficult to get this type of data in an accurate scenario. All right. So Kermack and McKendrick used this data to estimate beta to be equal to 0.017, and gamma is this. So in this particular case, actually most of them died, but at least they didn't transmit the infection to the rest of the community. Okay. So now, if we want to test the Kermack and McKendrick model with the data, what do we have? So that's what we'll be getting. So this is a curve by the SIR model, right? And these are the actual data, people who are susceptible, people who are infected. Okay. And these are in terms of months. So it spans like 5 months. And as you can see, the curve, right? It went up and down. Okay. And of course, that's because beta is quite low here. If beta is not low, we'll get, as you might suspect, we'll get something like this. All right, but now, so here, the data are kind of fine, but they don't look very, very accurate. But if we do a phase plane in terms of the proportion, the data are better, much better. Okay, so the system predicted by, is there any? Does beta and gamma extracted from historical data? Yes. Yes, that's a great question. So Wiley said, do beta and gamma are extracted from historical? In this case, yes. So they just want to test how their model do with data. All right, but they will depend on time. But for this case, it's supposed to be constant. Okay. All right. And what's the second one? So there's an inherent challenge in using all data parameters. Yes, there is indeed some inherent challenge. But for this case, it was one small community. So it happens that even if you take constant and it matches the actual value. Sounds good. And of course, this parameter will completely change if you have a large community in which people do not necessarily interact with each other that much. Okay. Actually, the reason why so the reason why beta is actually not constant in general, at least nowadays, beta is not constant because if we take a closer look at the flu, right? Typically, it's seasonal. So beta is not necessarily dependent, not only constant, but it has a very typical function. It's a sinusoidal function. It's a cosine of something, cosine of beta, cosine or sine of beta or something, depending on the parameters of people, on how people are getting affected. So it's definitely not constant. And the curve of the actual stuff right now in a large community is not as smooth as what we got here. This is quite nice, but it doesn't capture reality. And this one was good. This one is good because we have a small community and we have very good data that they compare the model with. Okay. All right. So now here we said one of the most important quantities is beta over gamma, how to make this less than 1 and why it's important. Actually, it's important because if you remember, right, we had I dot equal beta Sn Si minus gamma I. So if we take I out, what do we get? Beta S minus gamma. So at the beginning, right? What do we get? We get S number of susceptible is almost equal to the total population. Almost. At the beginning, because we have just few infections. So what do we got here? That implies I dot almost equal to I beta N minus gamma. So that implies the infection would increase if beta N over gamma is greater than 1 and decreases otherwise. So that's why this quantity, you can take N or S0, right? So if we have a lot of infected at the beginning, we cannot do the approximation S equal N, but we say S equal S0 at the beginning. So this quantity is called R0. So what does it mean? It means if we take one infected population, one infected individual, how many people this guy will infect over its infectiosity period? So let's say the guy will stay infected for 1 week. So during this week, how many people this guy will infect? Okay. Of course, it's an average. Technically speaking, it's not constant, but on average, it could be seen as constant. And this is called the basic reproduction number. Okay. So basically, so you have an index case, and this guy happens to be infected 2 people here, and this one is infected 2, and so on. So in this case, R naught is called 2, is equal to, and same for this. So in general, if R0 is less than 1, the disease will die out. If R0 is greater than 1, the disease will persist. So basically the goal is we need to bring R naught less than 1. At the beginning, in general, it's greater than 1. But we have to act on the different parameters to bring it below 1. Okay. All right, so now let's go back to our initial SIR model. SIR model, if we do that, right, we'll get if R naught is less than 1, then I goes to 0. If it's greater than 1, right, we have, it will reach a sort of peak here, and then it will ultimately go down. So this is the maximum value that we have, Imax. That's the maximum. Yeah, I should say Imax here. Okay. And then it decreases to 0. All right, and of course, now that we have n, S is this decreasing function, and its limit is exactly this transcendental equation. Okay. All right, so now, earlier we talked about like EM, right? So this was a small community, but later there's also the same authors that try to study plague that is somewhere in India. Okay, so they did exactly the same thing, and they tried to adjust the parameters to fit the model. And to get back to what Wiley said earlier, right? So it's a little bit better to choose your parameter so that your model will fit the data. But if you're trying to do a predictive analysis, either you have data and you see some trends, or you have to take an average and say, okay, these parameters will vary within some sort of range. Okay. And so these are the data, and this is actually the actual SIR model that we have. Okay. And so if you guys have some questions, so please either stop me or you can leave a message on the chat, on the Zoom chat. Okay. So let's try. So we saw earlier R0 is one of the most important concepts in epidemiology, right? So let's try to focus more on what it actually means. So beta times S0, that is the contact rate of susceptibles. You have some susceptibles, they move around, they will contact people. Right? And 1 over gamma is the mean duration of the infection. And of course, even this effective contact rate is times C times Q, so that's the contact rate times the probability in which a contact will lead to an infection. Okay. All right, so now, so typically we always have during an outbreak or a pandemic, we always have this curve. And you guys have heard a lot, flattening the curve. Okay. Typically, without any control, will have something like this without any control. But the problem is this is really bad. We need to control, or at least we need to take some actions in order to delay the peak. And not only delaying it, we need to bring the peak down. Okay. So it's 3-step. Okay. Reduce the initial growth, and then reduce the peak, and then reduce the final size. The final size is the peak. Okay. All right. So these are some of the main challenges. But again, the R naught is equal beta S0 over gamma. In order to bring the peak down, I mean, S0 we cannot change. Gamma we cannot change. The only parameter that we have control over it is beta. That's our only choice. But the problem is beta is a compound parameter, and it has many other related parameters within. Are there a stochastic model for representing beta to account for uncertainty? Yes, yes. There are many stochastic models, but this one, what we are trying to do here is simple deterministic one. But indeed, there are, I mean, mathematical models for epidemics have been developed quite extensively in recent years, and there's literally everything that you want. So now beta is the only control that we have. So one thing that goes into beta is the contact rate. If we reduce our contact with other people, we're reducing our risk of infection. Okay. So we can do it by ourselves, or it can be government imposed. I mean, the government has control over it. Not all of it, but a good effect on it. Okay. If the government, for example, shut down the public transportation, at least we cannot. We can still make contact, but will not be able to move as freely as we want. Okay. And that's where the term social distancing and all this are coming from. And the government has power in enacting on this. Okay. Now, what about the mobility and behavior and the spread of infection disease? How human mobility and our actual behavior will alter the dynamic of a disease. And we said earlier, right? We said pandemic is just an outbreak that is global. Okay. And by global, we mean there's some sort of movement between different communities. So that's where mobility and behavior are all affect our beta. So in order to reduce our beta, we need to reduce our mobility, and we have to have good behavior to reduce our risk of infection. So the goal is how to act on mobility and behavior to mitigate the spread of infection disease. Okay. And also, there are some cases for which we have some diseases that are shared with many species. So how we can reduce the connectivity between these different species to reduce the risk of spillover from one species to another. So these are some of the goals that epidemic models will typically address. So let's talk about mobility. So suppose that we have two cities, right? Part 1 and part 2. So we could either suppose that we have a short-term mobility between the two patches, or we could say, okay, these communities are far from each other, and any mobility could suppose that it's a long-term stay. So here we are supposing that we have urban community where we have people move from one patch to another. So I'm in Long Beach. I could take public transportation to downtown Long Beach, to downtown LA, and work and get back. So even if I'm spending like 8 hours in one place, it doesn't mean I live there. So that's actually very common with big cities. All right. So now we don't necessarily consider contact from the regular sense of the term, but we consider contact as a proportion of time you spend in one particular area. So if you spend a lot of time in a place that is with high incidence, your likelihood of getting infected is much higher than if you are spending your time in a less risky environment. Okay. So this is called the concept of residence time. Sounds good. Because the term contact in itself is not very clear. Of course, it's clear for some diseases like sexually transmitted diseases or vector-borne. But if we have an airborne disease like corona or the COVID, it's impossible to define what a contact is. Okay. And we suppose that each patch has a different particular risk. And this is actually could be measured. Right? For COVID, it happened recently. The hotspot are actually the restaurants where people go and dine in. And that's where people get infected the most. Okay. So now, what if we take the different risks and the residence time matrix or the residence time matrices to try to understand the dynamic of the disease? Okay. So typically, if we have this S, I, and N, okay. And here we have birth rate and we have death rate as well. And if you guys remember, right, if we are dealing with actually earlier, so if we are doing outbreaks and pandemics, so we suppose that the duration of these outbreaks are short enough that we don't need to include the birth rate and death rate. Because our life expectancy as a human, it depends on a country, but let's say it's 90. Whereas the outbreaks and the pandemics usually last around a couple of months or 1 year at most. Good. So we could neglect the vital dynamics. However, for epidemics, we need to include the birth rate and death rate because they are here to stay. Okay. So here we have the birth rate, or actually this is not only birth rate, but it's more like recruitment, people coming from elsewhere. It could be birth, or it could be immigration, or it could be anything. D is death rate. So we consider in each patch, and we try to study the dynamics of the model on each patch. Of course, considering that there's an interaction between these patches. Okay. So in each patch, right, we have this quantity of infected, and we have this quantity of population. And keep in mind here in each patch, J, we have all people from all different patches. So let's say we have Long Beach. We have, at any given time, we have a proportion of people from Fullerton, or we have a proportion of people from Long Beach, from LA, and so on, or from Anaheim. Okay. So now the proportion of infected will be this. So now a very crude SIS model with 2 patches will be something like this. And of course, as you can see, our beta or our contact rate now depends on the proportion of time susceptible spend in one particular area. Right? But not only that, it depends also on the risk factor of this particular patches. Because if you're spending all your time in a less risky environment, I mean, there's nothing to worry about. Okay. And so on. So this system could be, again, studied more rigorously, and it could be shown that if R naught is less than 1, the disease will die out. The disease dies out. And if R naught is greater than 1, the disease will, technically speaking, actually even less or equal. And then the disease will persist. Sounds good. So these are just a very short introduction, but there are many ways to expand on this, and it's expanded in very different directions. And so here we did mobility from discrete standpoint, but you could also take mobility from a continuous standpoint. And again, here we said susceptible, and that's it. You could also consider susceptibility in terms of age. So if you are younger, you are less likely to get the infection than if you are, let's say, above some sort of age. Okay, so it's possible to include many different features, but of course, it depends on exactly what you want, because the more realistic your model will become, the more unlikely that it will become, you'll be able to find, to study mathematically at least. Okay, and yeah, thank you very much. That's it. Thank you.
All right, that was good. Thank you very much, Bichara, for that introduction to mathematics of epidemics and pandemics. Any questions for the speaker? Wiley has typed a question. Do you want me to read it to you?
Yeah, go ahead, please.
Okay, as you make your parameters more local, presumably, the statistics available go down dramatically and the noise increases. Can this be accounted for when estimating your parameters?
Yes, it could. So basically, what is it? Yes, so here, if you don't consider mobility from in this case, it's fine. But if you are taking into account the mobility and the proportion of time people from one patch spend to another, so you need not only to incorporate to find ways to estimate this, which is in most cases it's not necessarily easy, but it's possible. The proportion of time people spend in one particular patch, that's possible, at least in developed nations where we have cell phone tracking and all this.
Okay. I have Sean's hand is up. Sean, did you have a question? No.
Yeah, I do.
Matt, why don't you go ahead and ask your question if you don't mind?
Okay, sure. Hi, thank you. That was fantastic. The model, however, sort of assumes that the recovered population stays recovered. And there are several different cases where that may not be true. If
Yes.
that's not true, I'm sure there are models that include that.
Yes.
How significant an impact does that have on whether a disease becomes an epidemic versus?
Yes. Thank you. So if we get back to what we did here. Yes. So here people are getting recovered, but if you are recovered, you are what's called again? If you get recovered, you become susceptible again. Sounds good. So basically, and here we've seen that we have you either go to 0 or I could go towards some sort of value, right? So that is because we are injecting the susceptible population from the infected. However, if we suppose that this is not possible, or let's say, let me take another example. Yes, so right. So here we have beta Si, gamma, and suppose that we have something like this, right? Let's say, I don't know, nu or. So in this case, S dot would be minus beta Si, I dot equal beta Si minus gamma I, and R dot equal gamma I, let's say. I'm going to suppose that we don't have this for now. But if we add it, nu R. Right? So if we don't have this, what do we get? What we'll be getting is the susceptible population will always decrease. And that's actually the best case scenario. I mean, you could hope. Basically, everyone will get infected and they will recover. And the infection will die out. I mean, it will kill some people, but but ultimately, I will go towards 0. It does a peak and will go to 0. But if we have, and because, yes, so let me do the curve. So this will be our I. And let me choose another color. So this would be also our S. And our R would be something like this. Wait, correctly. Yep. Or R would be R. So everyone will recover. Everyone will get infected, but they will all recover. However, if we are adding something like this, plus or minus mu R, in this case, we will end up having an equilibrium where there will always be infection. And the certain population may not, there will be always a certain population who are not infected. Make sense?
So that effectively guarantees that it sticks around.
Yes, yes, yep.
Thank you.
You have more questions. I think Sean is asking, does the spatial complexity generated from these models inform the kind of national strategy for flattening the curve that we should adopt?
Yes, because now if you have different patches, right? And these patches are interconnected, right? Patch 1, patch 2, patch 3. So we have one global R naught for all of them, but also we have R0 P1, R0 P2, and R0 P3. We have a global R naught, but also we have each local one. And of course, all of this depends on the mobility between the patches. So I suppose that I'm here and my list is right now I don't have enough infection. And I've heard that, hey, in patch 2, they have too many infections. Okay, I can cut this. Sounds good. While still maintaining some sort of a balance between P1. I could also cut between P1, but the problem is I need some sort of mobility so that the economy will go on and things like that. So we don't want to go drastic. But again, it depends on how it depends on the burden of the infection in patch 1. But if there is sort of coordinated effort where, hey, this patch is a source of the infection and this one is a sink, we need to coordinate in order to reduce the disease. But there's also some cases for which back when Ebola was a thing. So there are some, let's say, cities that have very high number of infection, and all the cities around cut all communications between the city, and actually it was a government sponsored. The problem is in that city, even people who are healthy, they are poised to stay there. They don't have any other choice to move. So they might sit there and get infected. Whereas if they have an opportunity to leave, they might leave without getting infection. So it happens that drastic measures could lead to some case where it will be worse. I mean, maybe not for your own city, but if you take overall outlook, there are some people could be saved without the quarantine or the cordon sanitaire, as they say.
I think you had one other question that we somehow missed, and that's Andres asking, is it possible to predict if or observe when a pandemic, at what point a pandemic becomes an epidemic in using your models?
Yeah, so if the epidemic will persist enough so that people who are born in the outbreak grow up and transmit or get the disease. So in this case, it will become an epidemic. So basically, it depends on the lifespan of the outbreak. If it's long enough, even if at the beginning it was an outbreak, if it stays for a long time, it will become an epidemic.
All right. Any other questions for the speaker? Wonderful. Let's thank him one more time.
Thank you very much. Thank you, guys. Thank you.
Thank you for the wonderful presentation. And thank you, everyone, for taking time from your Friday afternoon coming to this award-winning presentation. We will have some of our students presenting some data on COVID-19 soon. And next semester, CCAM will host multiple workshops on Python, R programming, SAS, and also machine learning. Thank you so much. The recording of this session will be available soon through CCAM's website, and I'll send announcements in that regard. Thank you again.
Thank
Have
you.
a wonderful weekend and take care, everyone.
Thank you. Thank you very much. I appreciate it.